These days, many of us spend a lot of time on the internet. Growing interest in social media, the Internet of Things, and many other things that can all be summed up by exchange of information leads to an increasing number of internet users. First of all, let's have a closer look at that. Instant messaging and voice over IP services are only some features which acquire more and more users every day. Distributed data and computing power, like in clouds, gain more influence too. And there's a steady growth of the world's knowledge, which is also available from the internet. Thanks to that, there is instant help available in emergency situations and also educational help for school kids, students, and everyone else. By this, everyone can create new opportunities for everyone, like Google announces it. But there's still a question that's unanswered. How big is the number of internet users in comparison to the rest? And what is the global distribution of participants? In other words, who cannot share the advantages we gain from having internet? This map shows regional internet access rates per country in 2014. The color intensity of the locations represent the percentage of internet users in a certain area. The darker they are, the higher the penetration. When paying some attention to poorly developed regions, they appear to have barely support. Another remarkable thing is the exact distribution of the internet users. As you can see, poorly accessible areas obviously also suffer from low internet connectivity. To get an impression of facts, let's have a look at this diagram from Statista. From 2005 to 2015, the number of internet users worldwide increased from 1 to 3.2 billion, which makes a growth of 2.2 billion over 10 years. Let's say world's population will stay constant over the years. A linear extrapolation of the growth would show that not until 2035 there is a 100% coverage for internet. That's a long time to go. Probably it will take even longer due to difficulties in building up wide connections to remote and poorly developed areas where internet costs overtop monthly income. That means a cheap and more flexible internet solution is required to speed up the developing process and thus enhance global information exchange. Possible solutions for this problem were constructed from one basic idea: wireless interconnected aerial or space stations providing internet to distribution centers or end users on ground over a large distance. But realization attempts of different companies showed minor success.
In 1991, the Global Star project was founded. Its first satellites were launched in 1998 and the first core was placed in the same year. 2 years later, full commercial service with 52 satellites began. But after 2 years of service, Global Star filed Chapter 11 bankruptcy code. Until 2004, Global Star was completely reconstructed. With over 315,000 subscribers as of June 2008, Globalstar is the world's largest provider of mobile satellite voice and data services. Many industries make use of satellite telephones, satellite data modems, and satellite airtime packages from remote areas beyond the reach of cellular and landline telephone service. Since 2012, Globalstar has limited functionality over much of Africa, the South Asian continent, and most mid-ocean regions due to a lack of gateway Earth stations. In 1998, Iridium was founded. By using 66 active satellites, it could provide a total bandwidth of almost 30 kilobytes per second. Iridium could be used for worldwide voice and data communication, from handheld satellite phones and other transceiver units. The Iridium network is unique in that it covers the whole Earth, including poles, ocean, and airways. The founding company went into Chapter 11 bankruptcy in 1999 due to difficulties gaining subscribers. Their service was restarted in 2001. In the 90s, Teledesic was founded to build a commercial broadband satellite constellation for internet services. Low Earth orbit satellites were supposed to provide uplinks of 100 megabits per second and downlinks of up to 720 megabits per second. The original proposal was extremely ambitious, costing over $9 billion and putting 840 active satellites at an altitude of 700 kilometers. In 1997, the plan was already scaled back to 288 active satellites at 1400 kilometers. Mainly the commercial failure of Iridium, Globalstar, and other systems, in addition to bankruptcy protection fillings, were the reason for halting the project. Teledesic officially suspended its satellite construction work in 2002. But due to the high costs and low data rates, these systems are hardly applicable for widespread internet service. In 2013, Google came up with its own solution for the difficulties.
But how do we bring affordable internet to everyone? Maybe finding an answer starts with looking somewhere new, like up, and trying something different, like balloons. Yep, that's right, balloons. Because it turns out that if you use balloons, it's faster and easier and cheaper to give everyone the internet than it is to give some people the internet. That's why we're giving it a try.
This project is called Loon and is part of the Google X project group, what means that it is one of the moonshot thinking matters of Google. The mission goal is a network of balloons traveling on the edge of space, designed to connect people in rural and remote areas, help to fill coverage gaps, and bring people online. That means not only first-time connectivity, but also recovery after natural disasters. Why is it called Loon? First of all, it's short for balloon. And finally, the idea of providing internet access for an amount of approximately 4 billion people is an unprecedented and crazy idea. Project Loon balloons float in the atmosphere at 20 kilometers altitude. That is twice as high as airplanes fly. In comparison, Baumgartner's jump was from almost 39 kilometers. To travel, the balloons take advantage of the winds in the layers of the stratosphere. By partnering with telecommunication companies to share cellular spectrum, Google enables people to connect to the Loon Network directly from their phones and other LTE-enabled devices. The signal is then passed across the Loon Network and back down to the global internet on Earth. The inflatable part of the balloon is called envelope. They are made from sheets of polyethylene plastic and measure 50 meters wide by 12 meters tall when fully inflated.
Balloon. We are doing a ground-based inflation, trying to mimic what is happening in space.
When a balloon is ready to be taken out of service, gas is released from the envelope to bring the balloon down on Earth in a controlled descent. In the unlikely event that a balloon drops too quickly, a parachute attached to the top of the envelope is deployed.
Deploy.
Unlike weather balloons, Loon envelopes are superpressure balloons designed to stay up for over 100 days. The envelope is made of two balloons, the outer balloon containing a certain amount of helium or hydrogen, and the inner balloon, the ballonnet, that contains ordinary air. The more air a balloon contains, the heavier is the balloon and thus has a lower altitude. A custom-made air pump, also named the crotch, can pump air into the inner balloon.
One of these and you spin it really fast and you can move air. It's built up into a housing. Air comes in the bottom, it goes out radially, and then we direct it up where it interfaces with Dan's system.
The amount of helium should stay constant, but there is also some loss over the time due to diffusion. Here you can see the crotch in action. First inserting.
Let's start by pushing air into it.
And then releasing air by opening the valve.
Putting air in and out of balloons is not actually the only way to go up and down.
The greatest part of the payload of a balloon is a small box containing the balloon's electronics. It hangs underneath the inflated envelope, like the basket carried by a hot air balloon. This box contains circuit boards that control a system, radio antennas to communicate with other balloons and integrated antennas on the ground, and lithium-ion batteries to store solar power so that balloons can operate throughout the night.
The batteries are up top, and then there's some control electronics. The cellular equipment that delivers the signal, up to 30 megabits per second, is missing from this demo because Google didn't want it revealed.
The integrated avionics software is used to coordinate with mission control and perform safety checks, while flight sensors measure the balloon state and things like GPS position, barometric pressure, and temperature. The power systems regulate solar charging, power usage, and battery safety. On top of the electronics box, there is a solar panel. It is a flexible plastic laminate supported by a lightweight aluminum frame. It uses high-efficiency monocrystalline solar cells. The panels produce approximately 100 watts of power in full sun, which is enough to keep Loon's electronics running while also charging a battery for use at night.
We're essentially trying to fly a communications tower in the sky, and it needs to run 24 hours a day, 365 days a year, only on sunlight.
To set up in the balloon and balloon ground communication, some kind of antenna is necessary. Google keeps a lot of secrets regarding this technology, but the Loon US patent indicates radio frequency antennas as well as optical communication devices. The stationary ground devices of the network are represented by red balloon-shaped orbs, which actually are the Loon Internet antennas for end users. On the inside there is a patch antenna combined with a reflector that catches both direct and reflected polarized radio waves. To emit or receive different signals, the reflector is shaped in a way to be able to process signals from all directions inside the horizon.
So I can take it apart here and take out the antenna. There are cables that run down to the radio. There's a reflector here, and then the actual radiating elements up on the top. The green parts on the top are called a patch antenna. The patch receives both reflected waves that bounce off the reflector and go up into the patch, and direct waves, and those interfere constructively for the correct wavelength that we're trying to receive. The reflector and the design of this antenna, the particular shape that it has, determine the actual profile of the signal. And that's really important because the balloons are not at a uniform distance from the antenna at all times. It's different than a satellite dish. Most communication satellites are geostationary. They rotate around the Earth at the same rate that it revolves, and they basically stay in the same spot overhead. So the satellite dishes on the side of your house can be aimed in a particular direction and hit that satellite. With the balloons, they're drifting overhead, and a fixed pointing dish is not going to work. They'll be further away when they're not directly overhead, and then as they glide overhead, they'll become closer and then move further away again. So the antenna actually has to have more sensitivity off to an angle than it does straight up. That results in a uniform signal strength no matter where the balloon is overhead. This is what the Loon antenna looks like now, but we're not sure that future Loon antennas will look anything like this one.
Each balloon can provide connectivity to a ground area within a radius of about 20 kilometers. That is an area of about 1.3 thousand square kilometers. So it would take about 300 loons to cover an area of Germany, by the way. The communication is based on LTE technology with a data rate of single-digit megabit per second. This is about 3G speed. This protocol is defined in the IEEE standard 802.11. Thus, all LTE-enabled devices such as cell phones, tablets, and notebooks can connect directly to the Loon network. To keep the connection between moving loons, similar techniques as those in ad hoc networks are used. The currently used frequencies are ISM bands, specifically 2.4 and 5.8 GHz. And when clustered, every loon contributes to the provided bandwidth. Now let's see how the network operates on that features. The signal from the user bounces from balloon to balloon in the mesh network and finally to a ground station that connects the Loon network to the global internet. Currently only 5 bounces or hops in the mesh network are allowed. To route data inside the mesh, routing algorithms like Dijkstra might be used. The Loon US patent indicates that the communication between balloons and balloon and the ground station shall partly be implemented with optical communication as well as high bandwidth radio frequency communication. The optical connection between loons is no permanent link. It can be established and terminated if necessary. However, the possibility of an optical connection is determined beforehand. It also implies the possibility of special downlink balloons that hover above a ground station and provide high data rates. The following animated video summarizes the concept.
Balloons communicate with one another via optical communications using LEDs and lasers. They can also communicate via radio frequency links with ground stations. The communication helps balloons coordinate for efficient operation. The balloons travel approximately 20 km above the Earth's surface in the stratosphere. Winds in the stratosphere are stratified, and each layer of wind varies in speed and direction. By moving with the wind, the balloons can be arranged to form large communications network. Software algorithms determine where the balloons need to go. Then altitude of the balloons is varied to move each one into a layer of wind blowing in the right direction.
The ground station is a special station with connection to the internet for communication via high bandwidth radio frequency and optical links with the balloons. In the patent, it is also stated that the ground stations of the local internet service provider shall be used as ground stations for the Loon Network. Furthermore, it suggests the usage of satellites as an alternative to connect to the internet. For the critical listener, the dynamic structure of the Loon Network appears to be a disadvantage, since it is difficult to maintain the coverage of a certain area. But it also has advantages to have traveling balloons. Higher bandwidth demands can be satisfied in a short time by clustering loons above the area. And the adoption to changes of the underlying topology can be carried out quickly. To get an impression of network sustainability, the following simulation illustrates a balloon network behavior under real-life conditions.
This is one of the balloon simulations I made. This is a simulation of a bunch of imaginary balloons and how they move in some real-world wind data that's available to the public. Each of these balloons considers what different winds are available at different levels in the stratosphere and then changes level to catch whichever wind is most appropriate. The red dots correspond to balloons that are low down in the stratosphere, and the blue dots correspond to balloons that are higher up in the stratosphere, and the balloons that are changing colour are changing altitude. In order to change how the balloons are spaced out, I can control a bunch of parameters here. For example, I can modify parameters that control how fast the balloons can climb, how fast they can drop, how high and how low they can travel, and this allows them to catch different currents in the wind.
In the stratosphere, there are many layers of wind. Each layer varies in direction and speed.
To know what the winds are in the stratosphere, so we can surf those winds in order to go different places.
At 20 kilometers altitude, there are relatively low wind speeds between 8 and 32 km per hour with only little turbulences. Those winds can reasonably and accurately be modeled. Loon balloons go where they are needed by rising or descending into a layer of wind blowing in the desired direction of travel. By moving with the wind, the balloons can be arranged to form one large communication network.
Generated by my planning framework, we're trying to launch Australia. We're trying to launch out of Australia and to cover the coverage in Chile. And in this picture, you can see like this small, like a couple dozen balloons is coming out of Australia, heading over to Chile at different directions because the wind is actually going different directions. So this tool helps us to be able to predict the wind patterns at different times of the year. And we can also try to do this in various different ways so that we can launch balloons out of different cities.
To calculate optimal balloon routes, Google uses weather data from the National Oceanic and Atmospheric Administration. It provides updates every 6 hours for 16 days of wind data in the future.
Right now we're only flying a few balloons, but we're already gathering a lot of really exciting data that's helping us understand the stratospheric winds better. And as we have better understanding, that's enabling us to fly more balloons with greater confidence and provide ourselves with even more data. And so we have this ever-improving understanding of the stratosphere.
Using this data and a lot of computational power, Google calculates the path of every balloon continuously. Therefore, it also uses real-time telemetry in the closed control loop. Here you can see the output of the crazy simple planner algorithm. It is an heuristic spanning tree algorithm for route optimization, which determines the optimal destination path, where optimal means the cheapest cost for time to destination, altitude band, power consumption, or shortest path. In the following simulation, the shortest path is computed continuously and is indicated by the red route.
The black arrows basically points is the wind direction and the speed at that position. And as you can see, the red arrow is the movement of ibis as it flies with the wind. So besides the position, the altitude information, and the wind data, we also consider things like the battery power, the health condition of the balloon to determine the balloon duration while we're making this type of prediction.
Due to not 100% accurate wind and weather forecasts, the simulation data is modulated with some disturbances to get more realistic results. Once they are emitted, the crazy simple planner chooses the optimal path. One might think that the possibilities for balloons to travel are quite limited, but as seen in this illustration, on every node, a lot of new possible destination points for one balloon emerge. In special cases when there is need for high bandwidth support, the Loon Network is able to accumulate communication speeds by navigating several loons to a designated location and thus increasing the density of balloons in required areas. That means a high sensibility and flexibility in case of request anomalies like enormous social events or natural disasters. Also, the loon density over large bodies of water can be reduced easily, while still providing internet to chosen on-sea locations like ships or offshore platforms via satellite connection. The altitude of 20 kilometers has the advantage to be well above weather events, wildlife, and airplanes. But it also presents unique engineering challenges. The air pressure is only about 1% of sea level pressure, thus there is less protection from UV radiation and dramatic temperature swings, which can reach down to minus 80 degrees Celsius. But the reliability of the lithium-ion batteries, for instance, depends strongly on its temperature. Thus, a heater has been installed to keep the battery from getting too cold, as you can see here. To keep the batteries warm, Google now also uses a multi-layer insulation with space blanket material, styrofoam, and special formulated electrolytes and cathode materials.
So we've started to use this multi-layer insulation, which is a type of space blanket material similar to what goes on NASA spacecraft.
The energy for the heater is served by the battery itself and the solar panels. In combination, they can provide continuous power, even at night, to all components. That sounds a lot easier than it actually is. The incoming power from the solar cells depends on the balloon shadow, the atmospheric effects on the solar radiation, and the solar elevation, as illustrated in this picture. In summer, the sun is elevated much higher than in the winter. The elevation also depends on longitude and latitude. At small elevations, the energy density is lower, and thus the electrical energy collected by the solar panels is smaller. All these factors had to be included in the model to create a reliable predictor. This is a diagram comparing the results of the predictor, the blue lines, with the actually measured data, the green lines. Both lines coincide most of the time, which indicates an accurate prediction. Another challenge is to estimate the balloon's lifetime. It is basically given by the pressure of the helium, its temperature, and the amount of gas left in the balloon. The measurement of the temperature of helium at an ambient pressure of only 5,500 Pascal is a problem, since conventional sensors are based on convection. That's why Google engineers created a model of incoming and outgoing radiation to estimate the absorbed energy. This includes not only the radiation from the sun, but also reflected radiation from the Earth and clouds, the infrared radiation from the environment, emitted radiation from the envelope, and reflections of radiation inside the envelope.
Every morning when the sun comes up, our balloon gets warmer, and we stress it all day long with altitude control maneuvers, pumping air in and out, changing our internal pressure. And at night, our balloon gets very, very cold, and it becomes contracted and brittle.
These diagrams show the temperature, pressure and gas level of a balloon envelope during a time frame of 3 days. Here the blue lines indicate the actually measured values, whereas yellow lines indicate estimated values. Again, both lines coincide very well. The negative slope in the gas level is because of lost helium by diffusion. Due to the fact that the helium resources are limited, Google works on solutions that uses hydrogen instead of helium inside the envelope.
The fleet planning algorithm controlling each balloon on its route is not only a challenge in its complexity, but also in its computational intensity. The computational time is high enough to make even Google struggle to get the updates in time. When ascending and descending, loons cross the commercial air traffic. To avoid mid-air collisions, loons broadcast their position to ground. In addition, they are equipped with radar reflectors to be seen by radar stations and onboard radars. The direct visibility is increased by flashers. In any case, the flight agency is informed when a loon crosses the airspace. After showing you the technical details, let's come to the practical part with regard to some special Loon project milestones.
3, 2, 1.
Project Loon began with a pilot test in June 2013, when 30 balloons were launched from New Zealand's South Island and beamed internet to a group of about 50 pilot testers in Christchurch, Canterbury. However, the first successful superpressure flight was already in April 2012, with a duration of 4 hours and a traveled ground distance of 100 kilometers. The pilot test has since expanded to include a greater number of people over a wider area. Looking ahead, Project Loon will continue to expand the pilot, with the goal of establishing a ring of uninterrupted connectivity at latitudes in the southern hemisphere, so that pilot testers in these latitudes can receive continuous service via balloon-powered internet. By the way, the highest observed balloon speed relative to ground was 324 kilometers per hour. That is about the same speed as the fastest animal on Earth, the peregrine falcon. In 2015, Google announced a new milestone: a journey around the world.
So in our most recent long-distance LTE test, we were able to launch one balloon out of New Zealand, and it went around the world over 20,000 kilometers and be able to come in within 500 meters of ground distance and provide over 2 hours of internet connection.
But those achievements came along with some minor incidents. In May 2014, a Loon balloon crashed into power lines in a relatively remote area of Washington state. This incident cut the power to a small number of homes for about 5 hours. 1 month later, New Zealand's officials briefly scrambled emergency services personnel when a Loon balloon came down. The emergency services were contacted because it was mistaken for a crashing plane. In April 2015, a Loon balloon crashed in a field in Missouri after the signal was lost. And in September of the same year, a balloon crash-landed on a front lawn in California. Those incidents show that there is still some work to do, and Google agrees.
We deal with these competing requirements through an iterative design process where we create new prototypes every month, do extensive ground testing and test flights, and continue to refine our battery design to make sure we get the right answer.
Beyond that, Loon already has made great achievements and will probably be able to fulfill the promise to provide affordable internet everywhere and for everyone.
We've gone through a number of different internet providers to try and get reliable internet. It was so slow that we had to click on a page and go and find something to do for 10 minutes.
So can you give us a quick update on the launch?
Having a team from Google on our farm to trial this for the first time. It's been really exciting. Bingo.
Yay!
And that was fast too. To be the first person to do that is a little bit cool as well.